All right, hello everyone. I just wanted to make a quick video to review the relationship between the Gibbs free energy and the equilibrium constant that we were discussing in class, and hopefully clarify any confusion that I created, and also to reemphasize what I had put in the email that I sent everyone. So we're going to use this graph. So basically, by plotting this non-standard state delta G that we talked about versus the reaction quotient Q, that relationship can help us then find how the equilibrium constant is related to the standard free energy. So just first of all, hopefully we remember from class that we said this delta G equals the non-standard state free energy. And then, of course, delta G naught that we talked about in Chem 1B is the standard state free energy. And then when we say standard state, we talked about how that means we are dealing with gases at 1 atm or solutions that are 1 molar. Right, and since we're only going to be dealing with equilibrium reactions when we're talking about the equilibrium constant, we only need to worry about either gases or solution state species. That's the first thing we wanted to review. And then also wanted to review this Q. So remember, Q is this reaction quotient. And it equals basically concentration of products over concentration of reactants, just like our equilibrium constant. And of course, you would raise these concentrations to the power of their mole coefficient. And this is essentially giving us what the ratios of these concentrations would be at non-equilibrium conditions. Now, of course, if we're at equilibrium, then we know Q would equal K. So the Q could also represent an equilibrium state, but usually we would use Q to represent something that's not at equilibrium. All right, so those are just kind of some of the definitions that we kind of talked about in lecture that I wanted to clarify. Now, the last thing before we start looking at this graph is back to this idea of this non-standard state free energy. So we can imagine, hopefully, that if our delta G, so we are at some non-standard state, if that is a negative value, that means that is a spontaneous reaction, right? So remember, negative values of delta G means the forward reaction is spontaneous. Which of course means that the formation of products is favored. And then if we have a delta G reaction, non-standard state, that's positive, then of course that means the forward reaction is not spontaneous, or if it's an equilibrium reaction, the reverse reaction would be spontaneous. Because now we're talking about equilibrium, we could have the reverse reaction take place. So this would be the formation of reactants. Is spontaneous or favored. And so this is basically telling us that if we observe these non-standard state values of delta G, the reaction is changing. We're seeing that the reaction is not in dynamic equilibrium. It's changing either towards formation of products or changing towards formation of reactants. Now, of course, if we observe no net change in the reaction, that would then indicate that delta G equals 0, right? So that means we're not seeing any change in the reaction, neither the forward nor the reverse. Reaction is favored. There's no net change in concentrations. So that then would indicate that if we see that this delta G non-standard state is 0, that means we're at equilibrium. That's an equilibrium state because there's no net change. So that's going to be very important here in just a moment. Okay, so, and hopefully that kind of correlates with our ideas of equilibrium that we've already talked about. So forward reactions being spontaneous would have, which we'll see after we're all done, will correlate to large equilibrium constants. Reverse reactions being spontaneous will correlate to smaller equilibrium constants. But for now, we're just focusing on this, what we're observing at any moment in time with this delta G non-standard state. Okay, so now we can look at this graph. So hopefully you can imagine we could measure these delta G's at non-standard states using thermodynamic quantities. We could measure the enthalpies and the entropies for whatever particular reaction that we're dealing with, and using the specific temperature, and we could find that delta G non-standard state. We just have to track those thermodynamic properties at whatever conditions we're using, and then we could measure Q. So we could measure this reaction quotient by just looking at the concentrations of product and reactant that are present. We could calculate Q, and we could then just plot Q versus delta G. Now, if we do that, it turns out we would get a nonlinear function. So what we found, or what researchers have found, is if you take the natural log of Q and plot that along with delta G, so plotting delta G as a function of natural log of Q, that gives us this linear relationship that you can see here. Okay, so this is going to be the critical thing that we're going to use to now come up with a relationship between delta G and equilibrium constant. All right, so the first thing is we're going to look at this data point right here, and then we're going to look at this data point here. All right, so first let's look at this equation, right? So we have this linear equation, and so if it's a linear equation, we know that y equals mx plus b. That's our linear fit. And so we can see then hopefully that the y is delta G non-standard state. And our slope is yet to be determined. Our x is natural log of Q. And here it says QP, so this particular graph was looking at a gaseous reaction, but we can just use Q in general. It would work for both gaseous reactions or solution state reactions. And then our y-intercept, B is our y-intercept, and notice that our y-intercept here says that delta G equals delta G naught. So we could say that that then would be equal to delta G standard state, delta G naught. And so the question is, why is this? Why can we make this assumption? Well, remember we said that at standard state, we have 1 atm, 1 molar. So at standard state, if we plug in 1 ATM and 1 molar for all of our products and reactants. And remember, even if we were to include pure liquids or pure solids, they would also have a concentration of 1. That's unity. So if everything is 1 for this standard state, then Q has to equal 1, because everything's 1 ATM or 1 molar. And if Q equals 1, natural log of 1 equals 0. So this is saying that if Q is 1, natural log of Q ought to be 0. So that would put us here on this, on the y-intercept. So x equals 0, natural log of Q equals 0. Okay, and so because now we're at this, so if we're at natural log of Q equals 0, and now we can see that delta G would have this value, but if it's at standard state, this delta G has to equal delta G naught. So this is just a particular case where delta G naught is equal to delta G. Now, the key thing here is that I misspoke in lecture. So just because we're at standard state doesn't necessarily mean we're at equilibrium, right? So, and it's a little confusing because sometimes people might think of, well, if you deviate from standard state, you're kind of changing your normal delta G, but that doesn't mean you're deviating from equilibrium. So you could be at standard state and already not be at equilibrium. All right, so that hopefully answers the question of why if Q is 1, K does not have to equal 1. So we're not necessarily at equilibrium at this standard state. All right, so but the key thing is, but now by knowing that the standard state Q equals 1, that now allows us to put delta G naught into our y-intercept, and that's going to help lead us to figuring out how we can relate delta G to K. All right, so now the last thing is the slope. It turns out that if we do this relationship, and if we were doing it with a gaseous reaction, it turns out that that slope would equal RT. So that's just been derived by experimentation. And of course, remember, R is 8.31 joules per mole Kelvin. And of course, T would equal 298 Kelvin, assuming we always do our reactions at 298. So generally, you'd want to use 298 as your standard temperature. And so now you can see that that's where this the slope would be present in the graph based on RT. Okay, so now let's rewrite this equation on a fresh screen. So since Q equals 1 is at standard state, our delta G has to equal delta G naught. Okay, so now we have delta G equals RT natural log Q plus delta G reaction. That's our Y equals mx plus b form. We'll just rearrange this to make it look like the more traditional form of the equation. Just move the delta G in front of RT natural log Q. And so now the last thing we can say then is, so we found that when Q equals 1, natural log of Q equals 0, that's delta G equals delta G naught. Now the other thing is, well, what about when delta G equals 0? So here we can see delta G equals 0 at this point on the graph. Well, we just said prior that if delta G equals 0, that indicates we're at an equilibrium state. We're not seeing any change in the concentrations of products or reactants. So if that is at equilibrium, we now know that the Q that we have must be equal to K. All right, so that's by definition, that's got to be the case. So now let's take this equation. If we're at equilibrium, we know that delta G non-standard state must be 0 and Q must equal Kc. And so now let's plug in. So now we've just said delta G is 0, Q is K, and we use the same equation. And now let's rearrange to solve for delta G reaction. And that's the form of the equation that we would arrive at. So now we have a direct relationship where we can relate the equilibrium constant Kc to our free energy. Okay, so now let's take this and apply it and see if this makes sense. Like, would changing the equilibrium constant give us an appropriate change in free energy? And so if you go to your PowerPoint slide, you'll see that there's this extra slide that we didn't quite get to in lecture. So let's just write down our equation again. So hopefully what we can see then is that if we have large values of Kc, taking the natural log of a number bigger than 1, you would yield a positive result. So large values of K would give you negative delta G. And then of course, if you take small values of Kc, numbers less than 1, right? So large values would be greater than 1, right? So now if you take the natural log of a number that's less than 1, you get a negative result. Negative times negative is positive. So small values of Kc yield positive delta G reaction. And you can see that here for these examples. So for instance, this redox reaction where copper is oxidizing zinc, we have a very large K value, so it's a negative delta G. Conversely, if we have this reaction where we're looking at the decomposition of sulfur trioxide, very, very small equilibrium constant, and so thus it's a positive delta G. And so then hopefully this makes sense, right? So small values of K means the reactants are favored. Positive delta G means the forward reaction is not spontaneous. So now we can see that relationship to how delta G and K relate to one another. Conversely, we now have a very large equilibrium constant, so products are favored. And then we see then that, of course, negative delta G means that that the forward reaction is spontaneous, which matches our K. All right, so I hope that helps. So we can now see that the equilibrium constant is indeed a thermodynamic property. So even though we derived the equilibrium constant from a kinetic argument, we used the kinetics of the forward and reverse reaction to find K. K itself is a thermodynamic property. It's related to the energetics of the reaction. And so what we can think of is that so it's just intrinsic. It depends on the reaction. So we can see here that these products, so having zinc 2 plus and copper 0, just must be more stable. These products are more stable. They have a lower potential energy than these reactants. So the forward reaction is favored. We have a large equilibrium constant. And then on the flip side, these reactants, so SO3, must be more stable than the products that we form here. And so now, if these reactants are more stable, you're going to get much less conversion to product, much smaller K. Forward reaction is not spontaneous. So I hope that helps, and I apologize if I kind of confused anyone in lecture, but I hope this will help you out, and we'll see you next time in class. Good luck.